Welcome to ETAP Global Conference 2021. My name is Human Ghafarzadeh. With my colleague Aslan Mojallal, we will present the ETAP Microgrid controller solution. ETAP Microgrid controller solution includes mainly ETAP Microgrid controller, the ETAP ICE gateway with high-speed real-time control. ETAP real-time server, SCADA, and HMI can also be used for advanced monitoring and control. In the proposed solution, ETAP Microgrid controller is responsible for performing supervisory controller as well as devising intelligent load shedding scheme. ETAP gateway is also primarily responsible to convert protocols as needed. In addition, the real-time control capability within the gateway allows to continuously receive ILA schemes from Microgrid controller and be ready to immediately act upon detection of unplanned islanding. One of the key features of the ETAP Microgrid controller is the availability of its digital twin that can be used as a true model of Microgrid controller within the simulation study. The digital twin can be used to basically for evaluation, testing, as well as fine-tuning the optimal controller settings. The ETAP Microgrid controller is based on model-driven technology where properties and connectivity of the system, the Microgrid systems, and their assets are known to the controller, and it can utilize them to perform the several tasks. Model-driven approach minimizes the number of settings required for describing the system and also for the control functions. And also model-driven approach allows utilization of predictive simulation to enhance or achieve advanced controller functions. The ETAP Microgrid controller offers several control functions which are most important for this application. For example, the grid-connected operation, including the economic dispatch and rule-based dispatch, which can be used to basically minimize the import power from the utility and limit the export power to the grid, and also can utilize to do peak shaving and reducing the cost of operation in the system. Planned islanding function, which can be used to basically to prepare the microgrid systems before basically systems goes to islanded operation by dispatching the assets in the systems or basically charging the batteries and so on. Unplanned islanding, which can be used for again, to devise intelligent load shedding when systems faces with unplanned islanding during a fault or basically maintenance or so on. Black start, which can be used basically to start resources and loads based on their rating, inrush current requirements, and more. Reconnect to grid, which can basically, the job of Microgrid controller is to monitor the state of the system, basically in the utility side. Once it detects the stable grid availability, it initiates the sync check relay at point of interconnections to systems goes to a grid connected mode. And also the active and reactive power control at point of interconnection, renewable smoothing, peak shaving, and other control functionalities. In ETAP technology, we develop and test the digital twin first in the simulation environment. And then once we validated the functions, once we validated the scenarios that we have, we can easily deploy the digital twin to the controller hardware and test it within the hardware in the loop test setup. ETAP also basically offers a real-time power flow and transient stability simulation at the microgrid scale, which the controller is in the loop. In this basically setup, the ETAP software runs in a PC and simulating a microgrid system by performing load flow or transient stability analysis. Basically, we are using, the ETAP uses a data hub, which is the basically hub to basically transit the measurement data from the slave, which is the machine that we are running the ETAP in the real time. It sends the measurement data through the MP3 or other protocols to the hardware, which is the ETAP Microgrid systems. At the same time, it is receiving back the dispatch commands and applies the commands to the assets in the system. I will show basically these demos in the next part of my demonstration. Also, ETAP offers a web-based user interface to provide high-level access to the Microgrid controller settings, metering, control, records, and maintenance. The interface can basically use to change the settings, apply new settings during the run in the field, and the grid operator can access to all the basically measurement data and the device basically records and so on. Also, in addition, the ETAP SCADA integrator provides the tools to configure alarming, state annotation, ETAP SCADA viewer interfacing, and many other advanced SCADA features. ETAP basically offers rugged machines with shock protection, fanless enclosure, and support temperature from -25 to 70 degrees Celsius. Depending on the application, depending on the complexity of the system or microgrid, we are offering advanced, basically advanced devices, such as the one that you see in the right-hand side, or basically less advanced one, the one that is in the left-hand side, basically. And as you can see, the ETAP Microgrid controller provides different protocols over Internet IP, such as DMP3, Modbus, IEC 61850, and many more. In addition, it provides hardware extension, which is ETAP ICE gateway for serial protocols over RS 485 and RS 232. If I want to summarize basically my presentation, as you know, as I mentioned, ETAP Microgrid control system funded based on 3 advanced technology: model-driven approach, digital twin, and also the software development framework for power system application. Using this technology, ETAP can effectively and rapidly customize and enhance its controller. Also, controllers offer several basically control functions, such as planned islanding, unplanned islanding, economic dispatch, renewable smoothing, reactive power control, and much more. In the next basically part of my demo today, I will first show an offline simulation using the ETAP basically environment. As you can see, this is the ETAP software. We have a microgrid systems, which it has a PV solar panel, batteries basically unit, and a load, a controllable load, and a backup diesel, which in the normal operation, which is a grid connected, this backup is not working, is not contributing in the system, but we can add this basically backup diesel once the system goes to islanded mode of operation. The systems connects to the utility or to the grid through this basically at point of interconnection. I just want to quickly go through the settings and the editor of these controller elements, and then I can show you the simulation results. As you can see in the controller element, this is for Microgrid controller, we can assign the assets and we can assign the elements that ETAP Microgrid controller needs to talk with them here, and we can add the associated device in this page. As you can see, we added the controller, generator, inverter, and so on, and we can select that this element is monitored or controlled or both of them. So once we added the associated devices, we can go to the setting or DLL page, and we can have access to the settings of the basically controller. As you can see from here, we can see the settings for active power control, reactive power control, renewable smoothing, transient to islanded mode, which is basically unplanned islanding function, planned islanding function, reconnect, and so on. And in each basically section, you have settings for this function. You can change the settings before the simulation, or you can do the basically tuning once basically you are doing the the planning or basically a study before commissioning stage. In this demo, I will show a couple of functions that we discussed earlier. First, I will talk about the economic dispatch function, rule-based dispatch function, planned islanding, and reactive power controller. Let me just run this case quickly here. And during the time that it is running, I want to discuss, basically explain the scenario. In this scenario, we have an ADMS control, which is advanced distribution management system, which can be a grid operator as well. It sends basically the planned islanding commands basically to the Microgrid controller. It means that in the second day, based on the settings, we set it to second day. It sends a command to the basically Microgrid controller, and it says that at 4 p.m. it sends a command that it says that at 9 p.m. we are going to go to the islanded operating condition for 2 hours. It sends the start time and duration of the islanded operation, and once the Microgrid controller receives the commands from the ADMS, it will based on the logic, it will tries to basically increase the state of the charge of the battery to basically increase the state of the charge of the battery to enable it to support the system during the islanded operation. And if needed, it will shed the load or ramp up the diesel generator if we need more basically diesel, we need more source, or if we don't have enough source, it will shed the load. And also right before the system goes to planned islanding, it will try to decrease the exchange active and reactive power at point of interconnection, makes the system ready to go to islanded operation. It means that it will try to decrease the active and reactive power exchange at point of interconnection. As a result, if systems goes to islanded mode, systems see less stress and system will remain stable. So if I basically if I show the simulation results in this case, this is utility active power. So this is the we are running the time domain load flow simulation. We are using the time domain load flow module, and we are basically doing the time domain load flow simulation for almost 2 days. And you can see that in the first day we don't have any action. We don't have any request to go to planned islanding or any unplanned islanding conditions. What basically the job of the Microgrid controller in the first day, which is the system is connected to the grid, is to do basically economic dispatch analysis and dispatch the units in the system, assets in the systems, to reduce the cost of operation. So you can see that we are importing power from the utility, but we are limiting basically the export power to the utility. As you can see, there is no there is no export power to the system, because I will show you in the inverter, the battery inverter, that during this time we are charging the batteries. And then once we have basically peak time, during the peak time, once we are importing power from the utility, the Microgrid controller will dispatch the battery to start discharging. As a result, it will basically reduce the import power from the utility, and it will reduce the basically cost of operation. The same scenario for the second day. As you can see, we are basically charging the batteries and we are discharging the batteries. But the second day, because we have a planned islanding request from the ADMS, right? Basically, before the systems goes to islanded mode, during the time that it is not a peak time, based on the logic, based on an optimization logic, the Microgrid controller is charging the batteries to basically increase their state of the charge. I will show you the inverter basically power. And then right before systems goes to islanded mode, you see that the active power basically export to the system or import is almost zero. So we don't have any exchange active power, so systems can easily go to islanded mode of operation. Let me show you the inverter, basically battery inverter active power as well. Battery inverter 1 active power. You see that during the time that we had basically zero export, we were charging the batteries. You see that we were charging the batteries during the time that we had more generation than load in the system. And at the same time, during the peak time, the Microgrid controller dispatches the batteries to start discharging. As a result, it helps to reduce the basically import power from the utility during the peak time of the day. Same for the second day, and you see that first we are charging the batteries for planned islanding scenario. Once the controller receives a planned islanding scenario, basically a schedule from the ADMS, it starts charging the batteries, as you can see here, and then start discharging or ramp up the battery to reduce the exchange power at point of interconnection. Let me show you the reactive power, basically, reactive power of the utility, because I want to show you the reactive power function as well. So this is the reactive power exchange at point of interconnection with utility. Let me show you the settings for this case, and then we can see the results. For reactive power, as you can see, we have a bunch of settings. We can define basically different active modes based on the time, or based on the basically based on the mode, or based on the time. Here we selected 3 modes of the operation in 3 times, at 0, 1, and 2, basically during the day, basically 12 a.m., 1 a.m., and 2 a.m. And we have, for each mode, we can select different basically control mode. For example, here we selected reactive power control mode. And here we can set the ramp rate limit, and we can set reactive power reference. For example, here we set reactive power 30 kilowatt at basically the reactive power for at point of interconnection. And for the second mode, also we have reactive power. We want to reduce it to 15 kilowatt. And then in the mode 3, we will again increase the reactive power to 30 kilowatt. So this is the scenario. Based on this scenario that we are running, we are doing the simulation. And here we can also set the elements, basically assets, based on their priority. It means that basically Microgrid controller will first use battery to basically satisfy these basically modes of operation that we set in the settings. And if we don't have enough battery, it will use PV, and then we can, if we have another source of reactive power, such as a STATCOM or other basically a capacitor, we can set it here as well. So everything is based on priority that we set in the settings. So if we check the simulation results, you can see that the first hour, it's basically the reactive power is almost, this is for single phase, it's almost 30 kilowatt. And then it reduces the reactive power to around 15 kilowatt, and then it goes to 30 kilowatt. The same scenario for the second day, basically. So as you can see, the Microgrid controller can effectively control the reactive power, active power at point of interconnection based on the modes of operation that we can set in the settings, or based on the commands that it receives from the ADMS or grid operator. So this was for the basically the simulation study that we do. As you can see, it is very easy to do the simulation in basically ETAP. It's the exact digital twin of the controller hardware that we can use in the field. Once we do the once we did the simulation and we we validated the results and we see that the results are acceptable, it is very easy process to deploy this logic to the control hardware, and it is very straightforward. And once we deploy the logic into the hardware, we can do hardware in the loop tests as a second stage of testing. And once we finish with the hardware in the loop tests, we can use the same hardware in the field. So in this next part of my demonstration, I will show you basically a real-time simulation scenario that in this demo, we are using 3 different machines. One machine is obviously is a control box, which we deploy the controller into that box, which is our hardware. It is working as a Microgrid controller, and it is our master. The second machine that we have is this machine that we are running the ETAP in real time. We are running ETAP transient stability, but in real time. It means that this is our slave. We model the system in the ETAP. We are running ETAP as a real time, and it basically runs the systems. It runs the transient stability analysis, and it provides the measurement data through data hub and DMP3 protocol to our master, which is the Microgrid controller. So ETAP runs as a slave, provides the measurement data to the master, and at the same time, the Microgrid controller sends the commands and dispatch the units, and data hub receives that commands and applies to the assets in the system. And we have the third machine, which is our HMI. As you can see, this is the HMI for that particular system that I showed you earlier. We have the same assets in the system. This is the Microgrid systems. It is really comprehensive. You can see for each element, you can see the data, you can see the settings, you can see the exchange power, voltage, and so on for each element, solar, PV solar systems. You have access to all the data that you can measure from the field, or you can get from the ETAP real-time simulator. You have access to all the those assets in the systems. We have also a trending page. We can see the signals and everything, trend of the signals in this page. And this is the overview page with all the information. Let me, for this scenario, we already deployed the controller in the box. Box is running, Microgrid controller is running in the box. What we are going to do first, we are going to run the slave, which is our transient stability simulation. So we are running the slave here. And as you can see, once we run the simulation, we will see the measurement data in our HMI. You can see that, for example, in this scenario, the PV, the solar panel, is supplying 10 kilowatt active power to the system. Battery is discharging 6 kilowatt. Load is 90 kilowatt, and as a result, we are importing 74 kilowatt active power from the utility. So this is the normal operation of the system. System is running as usual. It is grid connected, and we don't have any fault or any event in the system. Microgrid controller is doing the economic dispatch behind the scene, is doing it's the main function, it's running the main function behind the scene. So in this demo, I will discuss 2 control functions. Unplanned control function and the reconnect control function. These two basically functions we usually use. Basically, the Microgrid controller use this function when we have an event or when we have a fault at point of interconnection. Let's say we have a fault in the point of interconnection in utility side of the system. As a result of the fault, relays in the basically point of interconnection will open the breakers. And as a result, system needs to go to islanded mode of operation without any pre-notice or any basically information from this condition. So what is the job of the Microgrid controller system? Microgrid controller systems has a basically unplanned islanding function. In each iteration, even during the normal operation, it will basically it is running a logic behind the scene, and it basically inform the ILS gateway in each iteration that if systems at this point, if system goes to islanded operation, how much loads need to be shed or how much generation need to be curtailed. And the ILS gateway is already basically knows what is the action if systems goes to unplanned islanding. So the Microgrid controller iteration basically sends this information to the ILS gateway, and ILS gateway basically knows in advance. So once the systems basically see an event, see a fault, let's I open this basically breaker here. It is very easy to basically trip the breaker using this interface, HMI. We will open the utility breaker. Let's open the Microgrid also point of interconnection breaker. Let's say we have a fault in the system. Breakers open. Oh, sorry. Let me see. If I see. Okay, so we open the breakers, systems goes to islanded mode of operation. Right now, system is in islanded mode of operation. What happened? Basically, system, you can see that the frequency of the system is around 60 hertz. The voltage of the system is around 1 per unit, 220 volt. It is 219 volt, and the battery, which is the grid forming source in this scenario, is basically controls the voltage and frequency of the system. By basically, you saw that the battery were discharging 6 kilowatt, but once systems goes to islanded mode of operation, it increased to 80 kilowatt. We are using 10 kilowatt from the PV, and we are basically supplying the load. In this scenario, basically, we didn't need to basically shed the load because we had enough sources in the system. Even we didn't bring up the backup generator because we have enough state of the charge. We have enough the basically battery and PV in this scenario. So systems goes to islanded mode without any basically basically oscillations or so on. We can see the basically simulation results at other pages. So systems goes to islanded mode of operation. Let's say there's a fault clears. We basically systems get back to normal operation. The ETAP Microgrid controller monitors the basically the stability of the basically the status of the systems in the utility side. Let's close the basically breaker at utility side. You can see that once we close the breaker at utility side, right after that, the Microgrid controller will initiate the basically sync check relay in the system, and the sync check relay will basically close the breaker once the system is once that basically is a good time, and systems will basically again move from the islanded mode to the grid connected mode without any basically oscillations or instability. So these are two other functions that we discussed today: unplanned islanding and reconnect functions. I also show you other functions in the system. So as you can see, we are basically ETAP provides a really comprehensive solution. We are providing a digital twin which can be used to basically to test the Microgrid controller in the software environment such as ETAP. We can do all this basically planning studies, all the basically studies first in the ETAP simulation. Then we can use basically ETAP real-time simulator as a basically to do the hardware in the loop tests. ETAP real-time simulator uses the transient stability analysis or time domain load flow basically modules to run in real time in 1 second scale. And it basically provides the information, the measurement data through the MP3 to our basically Microgrid controller box. And at the same time, it basically receives the commands from Microgrid controller through the DMP3, and it applies the commands to the assets in the system. So we can easily do hardware in the loop tests. And once we validate the simulation results and hardware in the loop test results, we can easily use that hardware in the field. And then we have access to the ETAP basically web interface. The grid operator can use the web interface to monitor the systems, to change the settings during the runtime in the field, and also get the records and everything, or deploy the controller, basically logic and so on. If I basically show you our web page in ETAP, basically the global conference website, you can go to the basically exhibit hall, and here in the ETAP Microgrid section, first of all, please feel free to set up one-to-one meetings today and tomorrow. We are here to basically provide any information about the Microgrid controller solution. If you have any questions, we will be glad to answer them. And also, you have access to basically several documents that we provided in this web page that basically help you to get more information about our solution, about our Microgrid controller. And for example, this model, basically, this is a white paper that this is open here. You can basically go through this white paper. You can be more familiar with our product, with the solution, with the functions that ETAP Microgrid controller provides, and so on, basically. Thank you for your attention. I think right now, if you have any questions, Aslan, please, if there is any questions, please let me know and we can answer to your questions.
Thank you, Human. Thank you very much for the presentation. We have a couple of questions that I really appreciate if you can answer to.
Sure.
The first one, during your slide, you mentioned that the microgrid controller and the controller element in general are model-driven. Mm-hmm. And I was wondering if you can speak more about that and see, for example, what are the benefits that it will have?
Yeah, the main benefits of a model-driven approach or technology is that the Microgrid controller, or basically the controller in the systems, have already access to the connectivity and basically the settings of the assets in the system. It means that we don't need to define the whole Microgrid systems in the basically using the settings in the Microgrid controller interface or editor. As you saw in the basically my simulation, we have basically a bunch of settings. We have a setting page in this Microgrid controller, but these are all for the functions that we have, not for the assets in the system. So, because we are reading the settings from the assets, if we need to get, for example, get a rating of basically an battery or battery inverter in the system, the Microgrid controller have access to these settings through the basically protocols, and we don't need to define it in the basically simulation. And also, we don't need to define the basically connections of each units in the, for example, the generator is connected to this bus or PV is connected to this bus. These are all available through basically through this model-driven approach, and Microgrid controller have access to all these basically settings, and it makes basically the simulation, the design, first the design and then the testing very easy for basically the engineers, that they don't need to basically take care of all these basically settings in the basically system.
Thank you. We have another question. Could you please answer to this one? How did the system determine that the BESS has enough capacity to account for inrush once the island is formed?
Basically, this is a really good question. For basically the when we are going to basically black start, the job of the Microgrid controller is to basically to calculate the enough basic the value of the power, active power or reactive power that we need to do the black start when we are bringing up basically a unity to the systems. And once it has basically this calculation, it can, before the systems goes to basically islanded mode of operation, it can charge. As I mentioned, there's a logic behind the scene that before systems goes to planned islanding or even unplanned islanding, it basically charges the batteries to basically maintain a certain state of the charge level in the system all the times, that once systems goes to islanded mode of operation, the battery can take care of the system during that hours, basically during the islanded mode of operation.
All right, thank you. The next question is that how about using historic measured grid frequency fluctuating between 60.05 and 59.95 hertz as a function of time, data to simulate frequency control, the microgrid? I think it's a long question. Let me rephrase it actually.
Sure.
How about using historic measured grid frequency data to simulate frequency control, the microgrid, and to see the effects of fluctuating load profile on the frequency? I think the question is that can you use the historic data and for the frequency to improve basically the response of the controller?
Yes, actually, for the simulation, as if you are familiar with the time domain load flow, we have basically a time domain page. We can use external data, external active power, reactive power data from the basically an Excel file. We can basically we can use those Excel files to basically dispatch the load, basically a load in the system, and we can basically use those basically data that we have, the historic data, and we can use it in the time domain load flow scenario or even transient stability basically analysis, and we can replicate that case in our simulation environment, and then we can run the simulation and see how basically the Microgrid controller as a secondary controller can react to this basically event in the system, and it can help us to tune the controller during the simulation.
Okay, thank you. And the next question is that what is the difference between microgrid and virtual power plant, I think, VPP?
Microgrid system, I think it has several sources of energy, such as PV. It can have wind system. It can have diesel genset. It can basically have it can have load and so on. And it is a small basically system, a small power systems. But power plant, usually we call a system power plant, which we have only one source of energy. For example, we have a PV utility scale PV systems, which only has PV units. And the job of the power plant controller is to dispatch these PV units to basically reach certain goals. For example, certain exchange rate power at point of interconnection, or do this basically frequency controller and so on. For power plant controller, we can also do the grid code analysis, and we can basically do the frequency, basically control, power factor control, and other control functions which are specifically defined or designed for power plant controller. We will have another demo today if you again go to our web page. We have another event today at 3:50 p.m. Pacific time zone. It is specifically for power plant controller. You can attend this power plant controller demo, and in that demo you can get more information about the ETAP power plant controller.
Thank you. The next question that we have is that are we assuming renewable energy systems as microgrid or a small off-grid system like ship electrical system?
I think we can consider both of them as a microgrid system. As far as we have a source of energy, we have basically loads in the system. We can consider those as a basic microgrid systems. And the microgrid systems basically can be very small, such as basically a small basic commercial unit, a gas station, for example. It can be a very basically a big system, such as a basically university campus or even a small city. We consider all these basically small and large systems as a microgrid, and depends on the complexity of the system. As I mentioned in my presentation, we can offer different control functions, and we can offer different also hardware for each function, basically for each system.
Thank you. The next question that we have is that what it takes to model a microgrid with all primary and secondary controllers included, if you can answer
that. From time perspective, you mean, or?
Probably like what are the technical parameters or technical things that we need to consider to model the microgrid system in general?
Yes. In general, basically, this is a simple design. Basically, for each system, we can design the system, the real system in the ETAP environment. It is very easy. We can use basically ETAP library to. If I go to the design mode, you can see that we have access to all these elements. We can put the elements, we can connect. It is very easy and a straightforward process. We can easily model the system in ETAP. And once we basically model the system, we can put the primary controller, as you can see, load control, BESS control, PV controller. Again, this is not basically a complex basically process. You can put the primary controller, and you can do some simulations to validate the load flow results, transient stability results before you apply the microgrid controller. Once the results are acceptable, you validated the results, you can add the microgrid controller and do the analysis. This is not a very basic, this is a very easy process. It is straightforward, and we are providing several documents to and explain each basically process.
Thank you. The next question is that the availability of active power, reactive power, or the inrush current in inverter manufacturer and inverter rating specific. Are there different models for the BESS built in the ETAP library?
We have basically we have a battery element, we have an inverter element, which we can use both of them to model the battery energy storage systems. And for basically BS control, the user can use the UDM, or you can basically use a BS controller, as you can see be used here. We can add a control element, as you can see here. This is a control element that it is new in ETAP, and you can basically use a battery controller logic. You can use that primary controller here and just set the settings. If I open the battery controller here, we have a part of basically a bunch of settings for each battery system. For example, operation limits, minimum state of charge, maximum state of charge, the rate of the basically active power, reactive power, and so on, basically initial SOC. And we can easily use the battery model in the systems to do our analysis or simulations.
Thank you very much. The next question is that microgrid is it necessary only for the injection of PV, wind, hydro, ESS generation in the grid, which I believe you answered, but would you like to illustrate more about that?
Can you repeat it?
Sure.
The microgrid controller is for injection of active power?
Is it necessary only for the injection of PV, wind, hydro, ESS generation in the grid, which I think you mentioned that it has other applications like load shedding?
Yes, we have much more functions. We are providing more functions basically. That's basically the main functions that we Microgrid's job is to dispatch the units, active power, reactive power in the system. But besides this, we are offering other functions such as basically, as I mentioned, planned islanding, unplanned islanding, renewable smoothing, and other grid connection, basically reconnect functions, and much more basically functions that make this basically microgrid very capable for different scenarios that we can have in the system, in the field, basically.
Thank you. The next question is that can we inject automatically the PV wind energy storage generation in grid without the microgrid controller in ETAP?
Yes, without the microgrid controller, you can set the set points for each unit in the generation page, or in the, for example, for PV, if you go to inverter system, you can set the set point here. And based on the set points that you mentioned here, it will inject the same value. Or if, as I mentioned, if you use a basically profile, for example, internal profile or external profile, it basically will use those profiles, and it will inject the active power, reactive power based on the profiles that you provided. Same for other units, same for the load, same for the diesel and other basically assets in the system. These are for time domain load flow. In transient stability also, you have the same basically pages. You can set the set points, and they will inject the set points that you set in the editor.
Thank you. So the next question is that how about creating algorithms using if-else statements and scheduling for islanding grid connection for the controller? What kind of blocks available in ETAP library for this? I think the question is somewhat that what are the capabilities of the controller? What logics can it handle?
I think you can answer to this question because you are very expert in UDM as well. I think we have UDM. Please answer to this question.
Sure, definitely. So basically, the controller element is functioning with UDM perfectly. So if you're familiar with UDM, you can have all sorts of logic in UDM, implement those. Yes, as Human is showing in the controller page in UDM tab, you can add different types of logics, and these are the logics that are available if you're more comfortable using UDM and working with UDM. But if you're more comfortable in writing the logics as code, there are provisions for that as well. So you can basically write your own code for write the logic for the controller. But as long as you want to work with the blocks, there are so many different control and logic blocks in the UDM of the controller that you can use. And yes, I think that is it. If you want to add anything to it, Human?
No, I think, yeah, as you mentioned, we have two approaches, basically, mainly. We prefer to write basically logics. We can basically, we already write basically several functions for this microgrid controller in the code basic environment, but we also provide this UDM capability that users, if for the other logic, for basically more simpler logic, which, as you mentioned, if condition logics, that it is simpler, you can use UDM environment, UDM editor, to basically connect the logics and run the controller using the UDM. Both are available in our product.
Thank you. So the next question is that do you have price forecasting engine in ETAP for the particular market, or I think in general, are there any do you use forecasting at all?
Yes, we basically in our Microgrid controller, we have a forecasting function as well. Basically, it uses historical data, the measurement data from the, let's say, past weeks or past couple of days or years, basically, to do the forecasting for basically mostly for basically active power, reactive power. For pricing, also we can have that basically we can use the forecasting engine for that application for that basically purpose as well. Yes, ETAP provides a forecast engine as well. Basically, ETAP Microgrid controller has a forecasting functionality. Basically.
Thank you very much. The next question that I think is already answered, but let me ask it here, so maybe people are not looking at their chat can benefit from that. How fast does ETAP take to simulate a 24-hour scenario with complex controllers? I know that you have worked with real-time and scenarios that take a long time a lot. So I think that would be an easy answer for you.
For basically pure simulation, which is digital twin, as you saw, I ran basically the simulation for 2 days. It took almost 2 minutes or less to do the simulation in time domain load flow environment. For basically a real-time simulation, it will take 24 hours because it is a real-time. If we want to do the simulation real-time, for 1 day simulation, we should basically run the ETAP for 1 day. And once it's finished, we can get the data, or during the simulation, we can use HMI to see the data, to see the measurements, or to final report, we should wait 24 hours. But I think the question is more for this time domain load flow analysis. And you saw that I just ran the simulation and it took less than 2 minutes to run for 24 hours. It is not that much time, basically. It is very fast.
Okay, I think you mentioned that controller is currently working with TS and TDLF. What is the difference between these two modules, and in your opinion, when we should use either one of those, transient stability and time domain load flow? Which one? What's the best use case for each one of them?
Transient stability, basically time step in transient stability is in the level of 1 milliseconds or less, basically. If you want to do basically very precise simulation, if you want to basically at the same time that we are testing the Microgrid controller, at the same time we want to see the basically the I can say the performance of the primary controller, for example, the battery controller or PV controller, we can basically run the transient stability. The time step is in a scale of 1 millisecond or less, basically. But in the load flow, it is around, we can set it to 1 second or less as well, but it is mainly in 1 second, 1 minute, or even hour scale. For Microgrid controller purpose, for testing and basically tuning the Microgrid controller, because the Microgrid controller is a secondary level controller. It is basically, it is not, it is a basically secondary controller, which is time step is around 1 second, 5 seconds, a couple of seconds. Both basically modules is basically good. We can use both of them. There is no basic preference to use transient stability or time domain load flow. But for sure, the transient stability is designed for very fast control, such as the primary control testing or other basically tests that we can do in rush current studies and so on. But the load flow is more for basically the simulations that we need to do for a couple of days, and this time step is in the scale of minutes or hours and so on. But for our application, Microgrid application, I believe that both are the same, basically.
Thank you. The next question that I think is a really interesting one is that is ETAP compatible with RTLab of OpalRT real-time simulators? If so, do you have any published case study for this? And I think we actually, there is an exhibit for
Yes.
OpalRT.
If you again go to the basically exhibit hall, ETAP Microgrid controller, you can see that we have basically a couple of events for the Microgrid controller. I'm not sure which one is that one. I think one of them basically we use OpalRT for doing basically real-time simulation. Yeah, for sure, ETAP doesn't have any limit that which real-time or basically real-time simulator we use. We can use Opal or other basically real-time simulator to do the analysis, hardware in the loop testers basically. But one of them is for basically for one of the sessions that we have today is for OpalRT simulation basically. Power plant controller plus OpalRT basically.
Thank you very much. So I think the rate of questions are slowing down at this point, and we are getting close to the end of this session. So thank you so much, Human. We will be looking for new questions as they come in and try to answer them. Thank you so much.
Thank you, Aslan. Thanks for supporting this basically demo. Please feel free to ask any questions during this demo or after that. As I mentioned, you can set one-to-one meetings with us. Basically, we would be very happy to answer those questions. And I think you have also access to our basically email address and our pages. Please feel free to ask any questions that you have about our solution, Microgrid controller solution or power plant controller solution. Thank you very much.